Okay, class, welcome to the first video lesson for Chapter 7. If you're watching this video, congratulations, you've taken a little bit of your time outside of other term work and working towards an independent project for this chapter. Some of the things you're going to need to know before you start Chapter 7, just to list them here, types of growth, linear versus exponential. You need to know the difference between direct and partial variation. You've probably finished arithmetic sequences and series by the time you've started viewing this video. So the difference between those two types of sequences and those types of series. Solving equations are some other skills that are useful, as well as I would say converting between decimal and percentage, which not listed here, but is a skill you need to have. So we jump in for our note on simple interest. Simple interest is exactly that. It's not a very realistic way of calculating interest. However, when you're filling in your worksheet here, the first paragraph tells you a little bit about some of the key terms. If you're investing or borrowing, someone is paying interest, and it's always the borrower. Okay, so in this case, if it's an investment, the bank borrows. If it's a loan, then you're the one borrowing. Either way, interest is calculated, and the way simple interest is calculated is very direct. It's just a multiplier of the original principal value, P, using the rate, R, and the time elapsed, T. So the simple interest formula, when you construct your note, one of the things you'll have to do at some point is calculate the formula for I. And I is the interest calculated as product of principal invested, the rate, interest rate as a decimal, and T is the time elapsed. Now, the time elapsed has to match the interest rate. So if the interest rate is per year, then the time has to be in fractions or multiples of a year. All right, and when we use this formula, we apply it directly to the principal. So in this case, a $1,000 gift, that would be your principal value P. And as we go through, this person is gifted $1,000 and invests it over 5 years. At the end of the first year, the amount earned in simple interest is simply I equals PRT. So it'd be 1,000 multiplied by the interest rate, which in this case is 0.05. So 5% of $1,000 isn't much. And the time involved would, of course, be 1 year. Okay, times 1. So we calculate that out and we give you $50. So you've earned $50 at the end of that year. Of course, that is now yours, and the original $1,000 was yours. So collectively, the amount, which is simply the sum of the principal which belonged to you, and the interest which has just been earned or as a result of someone else borrowing your money, is 1,050. Okay, so this would be principal plus interest. And it continues from there. We can fill in the rest of the table for 2 years, 3 years, 4 years, 5 years by just replacing different amounts for the letter T. So here our R would be 0.05 and our time is, well, we're using the letter N for years, as later we'll try to make functions out of this and sequences. But it's going to be using that same simple interest formula. So we'll pause here. You can fill in the rest of the table. Some of it has already been done for you in your textbook. If you're working out of Chapter 7 here, your textbook has this information on page 418. All right, so the calculation for simple interest has been shown. This is a linear pattern. The amount of interest is growing by $50 for every additional year. So that's our rate of change. The amount is also a linear relation. The amount is also growing by that same value. Now, whereas the simple interest can only be calculated when time has elapsed, the amount is a non-zero value because we always have that principal value that has been invested. So here we're going to look at the two different ways of representing the information besides numerically. We can go to algebraic form, and we can also go to a graphical form. So in your handout, you should have filled in at this point the introductory paragraph. You should have also filled in the table at this point, and now we're going to construct a graph from this. Okay, I have opted to use the graphing calculator to display the graph. I'd like you to construct the scatter plot here in the space provided. So here I'm just tabulating the years elapsed, the interest in column 2, and the amount of the investment in column 3. From here, we're just going to make a scatter plot, and you can put a title on your graph and label your axes, and I'll show the result of that plot. I've turned on plot 1. I'm about to plot amount versus time. And here, if you're following along in the textbook, the Investigate 418, 419 has you to graph that that pair of variables, so graphing amount versus time, and then we're looking at describing the trend and looking at some graphical properties. So here, I'm going to change list 3 for your y values, which is the amount, and then I'm going to set up the window. Okay, you may want to use a similar scale for your graph. Times ranging from 0 to 10 years goes well beyond the 5 years that we tabulated, and the amount no lower than 900 in this case, because our starting amount is actually more than 1,000. I've bumped my y-maximum up to 1,500 just to allow for a little bit of extra space there, and then I'm going to go down and make the scale $100 at a time. So when I graph that, here's my plot. If we look at this, we can see it's linear. From the table of values, the amount is changing by $50. That'd be the first differences. So that's the tip right off, that the relation type is linear. It also passes through somewhere on the y-axis, so it's not direct variation, it's a partial variation. So now we can start to construct some information in the rest of this worksheet below. So if we look down here, the relation type would be linear. We're plotting A versus time n. It's linear. It's a partial variation. Graphical properties, well, we know the rate of change is the slope, and that would be $50 for every year of additional interest earned. The y-intercept, in this case, the y-intercept from the table of values is not one of the pairs of values that's tabulated, but we do have the y-intercept here at the principal, which would be backing up one step, would be 1,000. So from that, we can construct the function equation. Okay, so I just changed my title a little bit, amount by simple interest, labeled my axes, drew my 5 points, and connected them with a straight line. Now in this case, if you're thinking about the type of sequence here, or the work we've done looking at types of functions, we've looked at discrete and continuous. Here you could invest for a year, or you could invest for a fraction of a year. And so this is a continuous function, so we can connect those plotted points with a straight line. When we look at the function equation, we're trying to connect this to a y equals mx plus b, because this is linear. So in this case, we've already got the values, so we can call this f of n equals 50n plus 1,000. That would generate all the points there. In that function value for 1 year would be 50 times 1 plus 1,000. So this generates our sequence. The sequence type in this case, because it's growing by addition, this is an arithmetic sequence. And we recall that arithmetic sequences correspond to linear functions. All right, so it's an arithmetic sequence. We know that the general term for an arithmetic sequence is first term a plus 1 less than n multiples of the common difference. So what I want you to do now is, we've looked at the function equation. Now I want to generate a general term. In this case, though, we have to remember that sequences start at term 1. So our domain here is that n is a element of capital N being the natural numbers, okay? So the first term is 1,050, and in our sequence we don't have a y-intercept. So we're going to now construct the general term using first term, common difference, and term number. Okay, well, if you've gone through the process here, the only values we have to load in are the constants, which are the first term 1,050. Common differences are first differences are 50, and the general term, we do not replace n because this represents any term in the sequence. The not so surprising result is that the general term, the nth term, is 50n plus 1,000, which is exactly what we obtained when we calculated the function equation based on a linear relation. Okay, so here, nothing really challenging about going from the numerical to the graphical to the algebraic. It all corresponds to linear relations in their function form, in their graphical form, and in their tabulated form. So you should be able to construct a fairly detailed summary of what simple interest is all about, having done some calculations, having used the two key formulas for simple interest. Define the terms interest rate, principal, amount. The main definition of simple interest is recorded in your textbook on 418 in the margin. It's interest calculated only on the original principal using that formula. And there's some final connections to make to sequence types and graph types. I want to go back and just read something I found on the internet. Well, as you can see, this website, investinganswers.com, gives a little definition of simple interest, shows how it works by the formula, and then the final statement there under why it matters, it states that simple interest is a handy, easy tool for estimating the interest earned or paid on a certain balance in one period. However, it does not take into account the effects of compounding, which is the process of earning interest on principal plus interest that was earned earlier. This means it can dramatically understate the amount of interest earned or paid over time. And if we go back at this point and look at our table of values, I'll explain what that statement means. What's meant by the fact that it drastically underestimates the amount is that when we look at compounding interest, we'll see that compounding interest has a different type of growth rate, and it's much more realistic to the way that investments actually earn interest. But we can look at the calculation for, say, a 3-year time period and see that the $150 worth of interest that's earned really there's no sense that the first 2 years counted for anything. The interest was only applied once to that initial principal value. Likewise, by the time we get down to the end of the 5 years, we do our calculation, it's as if, you know, the first 4 years hadn't nothing had happened, and the interest was just calculated once based on five years elapsed time. So there's no compounding, there's no adding the interest back in and changing the principal amount. The principal is always calculated at the $1,000 value. We'll look at 7.2 next lesson, where we see that the interest gets multiplied or compounded into the calculation as we go. So this is a simple way to just explore investments and borrowing money for loans. At this point, completing the table, completing the graph, and filling in this graphic organizer would be the expectation before you launch into maybe some of these questions, just to strengthen your understanding. Not a lot of class time is going to be given for the independent study, so it'll be up to you to kind of pick and choose questions that allow you to understand each concept before you move on to the next one.